Federico on position-dependent arrays. That was yours.
Hello everybody, I'm Federico from the University of Edinburgh. This is the work that I did to put together with Michel, which is there in the audience, one of my two supervisors from Glasgow, and Christoph, which is my main supervisor from Edinburgh. So let's first motivate the journey of high-performance code generators, although it has been covered quite a lot today. So parallel hardware is increasingly different, heterogeneous, and common, and this has different problems, one of which is that these are different real platforms, and it's kind of really hard to create solutions which are parallel and efficient for all these platforms, especially from one single source. The traditional approaches have been either you code it in some low-level C framework, but that's really hard, as we've seen, and complicated. And the other one is you can push this complexity into a library, like NVIDIA makes all these beautiful libraries. Unfortunately, it's really hard to cover the niche case if you do that, because you can't make a library for everything. So there isn't really a way of having an economy of scale, so to speak, of high-performance code. You are either are an expert or you hope an expert passed by. And compiler-based approach would solve this. If you had the great compiler who can generate you parallel code from a high-level source, then everything would be fine. And that's basically what we saw today in different cases with Accelerate, Futhark, and our own, which is Lift. Now, how does these things look like? They're mostly based on functional programming language. So a simple example could be matrix vector multiplication. You have some way of specifying your data. And then you write the functional programming. This is one of the many Lift syntaxes that exist in the world. Something like you have a matrix that has 2 dimensions, so of n, as the drawing shows. You have a vector, and then you're going to map for every row, and then for every row there is some sort of zipping together the element, mapping and reducing. Let's generate the approach we would use in many of these ones. And then a possible implementation in sequential code would be something like this. You generate for loops for the maps, and the compiler is smart enough so it does like flattening the array because you want to be efficient, and it generates the index. So this works. This is basically what today's been saying. However, the way it works, let's say on the type level, is that you can have, imagine your arrays to be sort of types. You can nest them. You can have an array of size n inside of arrays of size n. And then you can have data types arbitrarily, you can keep nesting it. And if you remember today in the keynote, there was a graph was saying how these languages are all living in a dimension of nesting, but a sort of regular nesting. So what if we want to go behind that? What if we want to do something better than just like n-dimensional tensors? Nice, but you know, been done. So let's talk about less regular data structures. So what are some of these shapes we can talk about today? Well, we have triangles. Like triangle matrices are a common enough use case. And you can imagine it's very similar to a rectangular, just with some slight variation. There is this kind of shape that come up in practice. I call it the head, body, tail. I don't really have a good name for it. Just saying, imagine you have a grid, and you want to do something special on the boundaries that is slightly different than what you want to do in the middle. So that is also an irregular shape. You think about it as an array of arrays, where the inside arrays are of different lengths. And another shape would be the trees, as we've seen before. The binary trees are also sort of, if you squint hard enough, you can imagine as a flat array where you can index inside. But you can also think of it as an array of arrays, where every array in their array is a layer of the tree. So these are some shapes we would like to model, but we can't really with the current status. So we can introduce a new concept, position-dependent array, of saying let's relax what our type system requires. Let's say that now the element type inside an array can be dependent on its index, on its position. And just to sort of do the minimum possible increment, to keep this very easy and tractable if possible, let's say that only the size of this type can depend on the context. And by size, I don't mean like floats and ints are different types, but arrays can have various sizes. So that's what I mean by size here. So this will, for example, be the type of triangles. So you have an array, it's a like 2-dimensional array because it's a triangle. The outer layer, this n, refers to the various rows, and the inner array is each a row. And now you can see the outer array is kind of like lambda, it's kind of defining a scope, where the index is in scope of the element. And inside your array type has its size depending on the same element, and the innermost type could also potentially depend on that index. I don't know now, it's like a variable. So when you see a type applied to an index, it means the type could depend on, it's like a function of the index. So let's look at some useful cases in practice, so maybe it's better examples. Okay, triangle matrix vector multiplication is the first one. It's very similar to the regular matrix vector multiplication, only the one is a triangle. So we expect the program to be quite similar. Okay, we use type to express the data type, but what about the operations, where maps are generally thought to be performing a uniform operation over their input. So the input is all an array of all the same type, and the output is all the same type, so you expect the map to do the same operation. But now it's kind of not going to be the case, because each row is similar, but it's different, it varies in the length. So we introduce a new type of map, which is very similar. The other one is a dependent map, or position-dependent map, that can say, I can do a different action, but only insofar as its position. So the type of map commonly is this one, and in Lift it is this one as well. You take a function from A to B, an array of A's, and you get back an array of the same size, but of B's. Well, for a dependent map, it's something a bit stranger. So the function has also a notion of where it is located. So it takes first an index, is I called nat, so a natural number. And this is kind of a type level parameter as well, because then the argument types are parametric in that I. So it's some type, A to B, but I can appear in A and it can appear in the result B. And once you have that, you can say my input is going to be a dependent array, and my output is going to be a dependent array, and whatever is the type inside, they need to be the same dependencies, the same functions, so B is the same B and A is the same A. And that is, again, a bit messy in the writing, but it's quite intuitive. If an array, if the triangle comes in, a triangle come out, and the shape inside could change, but that's about it. And source code-wise, it's basically the same source code as before. The only thing that changes is that you say depth map instead of map, and you're using a triangle type instead of a rectangular type, but everything else just follows the type, so everything else just slots in nicely. So that's for triangle vector multiplication. The second use case we have is stencil computations. So, what are these? In case nobody ever seen a stencil before, is this kind of program where you have an input grid, which is in blue, and a secondary grid, a secondary input, which is also in blue, and you're sliding the greenish grid over the blue grid. And now the question is, what do you do when you get to the corners? Well, one of the common solutions is to say we add some padding. So we pad, which is this elements, these white elements dotted. And the way you can express this in Lift is something like this. You have a primitive slide, which is basically sliding a window over the input, and you have some primitive pad, which is going to modify the edges in some sense. And the types of these are pad just says take me some element or some redirection function, it could be either case, and a size m, and I make you return you larger arrays. Oh, there was an input that is missing. There's an input array size n, and it returns you an array which is the same as the input plus some extra element. And slide is just saying, well, I slide a window, so I return you a view, an array which is an array of views of the various windows. And the compiler automatically can infer the sizes because it knows the inputs. So, and this is the code as it look like, which is, I think, much easier to understand. You take the grid, you pad the grid, then you slide the window over the grid, and you map a reduction. So this case is one-dimensional, but two-dimensional stencils are fundamentally the same because all these primitives can be combined in a way to scale to n dimensions. And there has been a paper at CGO about this that I invite anyone to go check if you're curious about it. So what's the problem? The problem with this approach is that now, since you have padded the grid, every time you're doing your operation in the map, you have to check, okay, is this element in the pad or is this element in the grid, right? Because you're only going to select the pad once when you need the pad and the grid when you need the grid. And this costs performance. And in reality, you know that when you're in the center of the grid, you're never going to be in the pad. So in practice, what many human codes would do, they would split their big for loop into like a head, body, and tail section, and they would omit the checks in the body and only do half of the checks in the sort of head and half of the checks in the tail. Well, that's exactly what we could do if we could split this in head, body, and tail. We cannot do it before because otherwise we're kind of lying. Our map is doing different operations, right? And you shouldn't. So what we can have, we can somehow partition, it's the name of a new pattern, that the original grid into this irregular three parts. And then we can only generate the check in the head and the tail. So we introduce a new primitive, which has a big type. It's called partition. It says, give me a number of partitions. Give me a function that for each index of the partition tells me how many elements there are. So for example, if I say 2 and I plus 1, I'm saying take my array, chop it in 2 bits. The first bit will be, well, put 0 in positive I, 0 plus 1, 1. The second bit will be put 1, 1 plus 1, 2, etc. And then it says you must give me as input an array whose size basically accounts for all the elements. So for all the partitions, the size of that partition, sum it all together, that must be the size of your array. Otherwise, some elements are missing, or you're partitioning too much. And then we'll basically return you what we want, the dependent array, the position-dependent array, because it's exactly what works out. So this is the way you can introduce dependence in the system. And if you compare the two programs, the one before without the checks, and the one after, the one before with the checks without partitioning, and the one after partitioning, so without the checks, all you need to do is to add partition, and partition accordingly just saying, oh, I have one element at the start, I have like one, n plus 1, 0. Yes, you have the should be 1 here, there is one element in the end, and then for everything else, it's just the size n of your grid, and then you just do the dependent map as before, and everything should work out. It does. The compiler can now reach on this area separately, because it just can see 3 different areas, and it can say, oh, when I'm in this area of the pad, the math that you gave me with the padding means I can only check this 1/2. And when I'm in the middle, it's never going to happen. So no checks are generated for the center. Okay, so this is the sort of type level changes, language level changes, but this includes some problems in the code generator. So before, we had flattened arrays, only these flat regular arrays, and it's really easy, as you say, to go from multidimensional regular arrays to flattened representation, because you just have to multiply all the sizes. But how do you do it? So that's how you do it for the regular case. But how do you do it for the position-dependent array? Because now all your functions are potentially arbitrary and strange. So the only thing you can do really is to say, for every possible combination of indices, how many elements there are. Which mathematically is saying for every dimension I have a big sum, where I'm basically computing all the functions, all the sizes. And the problem of this is that if you want to generate high-performance code, you have at least your indices better be sort of simple formulas that your C can generate, your C generator can generate. You don't want a for loop or something else for your index computation. And before we could easily inline what we had, but now we cannot inline, because now if we generate a big sum, like what is it in C? How do I represent a big sum, right? Cannot do it. So the native approach is say, let's inject for loops in our code, and every time I need to access something, I generate a for loop, and I compute the index by it, which is obviously completely insane as far as performance goes, like it's a non-starter solution. So, but we can do much better. So we can use the knowledge we have from math, that there are closed form formulas. We can look at some big sums, and we can say, oh, but in reality, this is actually equivalent to some closed form. And we know several of them from mathematics. So, for example, if we see this formula, we know we can just replace it with that. We don't really need to generate a for loop in this case. So that's fine. And can we create a system that basically using some of these primitive rules and some other more complicated rules that split formulas and move formulas around, you can generally take a formula with big sums and sort of hammer it into a shape that you want. And in practice, this actually works. We had to implement some simplification for some very unusual things, such as if-then else's, like what do you do if in a sum you have an if-then else, how do you move the if-then else out of the sum, or how do you eliminate it? But if you can walk through that sort of problem, then yes, this works in practice. So I cannot guarantee in all the cases, because who knows, right? But in practice, when you have triangles, when you have these head-tail things, trees and things like that, the big sums go away, and then hence it becomes acceptable performance-wise. One example of this worked in practice. So if I want to offset into a triangle, given row ID and column ID, well, that would be the formula that the generator sort of naively comes up with. And then we say, oh look, that's +1, we can move it outside of the sum. So that's the way it works. It's a bit different, it's a bit deceptive, because all the sums start as 0, so all the formulas are similar to the ones people know, but they're kind of shifted around, but they're correct. So move out the constant. Then the big sum gets turned into a, using the formula I just showed, can be turned into this sort of thing. And that it would be good enough already, but we can actually combine the terms together and move the row ID inside. So we have a system within the compiler that does basically symbolic algebra and can deal with these cases. So let's go to the evaluation part of this. What do we have? First thing we tried was the triangle matrix vector case. We tried this versus cuBLAS, which is I think the state-of-the-art best implementation of BLAS for NVIDIA devices. And the graph here shows the performance of the speed up or lift compared to cuBLAS. So 2.5 means 2 times faster than cuBLAS, and this means almost the same as cuBLAS. So it works in practice. It seems to be very fast. Now, why is it very fast? I don't know what cuBLAS does, so I cannot really tell. But I do something slightly more, what we do in practice is slightly more sophisticated than what I showed on the slide. You have to, it's not as simple as saying just depth map for each row, for each column. You need to be smart, you need to be able to use the parallelism, the word groups and the threads. And there is some work there, so I'm not saying it's just the compiler is a genius, but it can get you there. So that's what I'm saying. At least the technique doesn't cost you performance. And if you do the stencil boundary check, so this is lift versus lift. So without the checks, the speed up relative to without the checks. So if you remove the checks, how does your speed up go? Well, we get a very good speed up in some cases and not so good in others. We have, so for the 3x3 case, so this is the grid, the stencil grid side, the green grid, the side of the green grid. And the side of the grid influences what's the ratio between elements in the pad to elements within the body of the grid. So you would expect that the bigger your grid size, the more benefit you have. And in the 3x3 case, it's probably the case that the compiler does some unrolling, and it is smart enough to figure it out, even for the unoptimized case. And for the top end, I don't really have a good explanation. I think I've talked to people, and we have maybe got to the conclusion that it could be to branch prediction. That is big enough, there is enough space in the middle that even the branch predictor of the system with checks will start to figure out, oh look, we are really in the middle, I don't need to check all the time because there is enough span to train the branch predictor. But it's again, it's speculation. So summary, if you work, this position dependence can be used to express these structures and maybe move us a bit up in that graph that was shown in the keynote. So maybe lift, and this technique, although it's implemented with lift, there is nothing lift like essential in this technique, so it could be used by other code generators to express other kind of structures like that and make us a bit more expressive. And it costs no additional cost or runtime, so it's still performant. Of course, this is only dealing with dense data structures, and the normal question, the natural question for me was, once I can express these less regular structures, can I express proper, irregular, sparse data structures, or sort of sparse matrices, things that are input dependent, and can you make the compiler aware of this? And I think it's possible, and we're working on it right now, and there are some preliminary results. It can be expressed. So position dependence can be used as part of this framework as well. And thank you, I'm done. I speak very fast.
It's a workshop, so time for questions.
So,
Please go.
Yeah, I want to continue with the stencil speed up. So I'm a little bit confused about, so the bounds check you're eliminating is that when you need to read an element from the stencil, you first check whether you're out of bounds, and if you're not, then you read it.
yes.
So really what you're saving, you have to read a word from memory, and you're saving a single branch when you're reading the word.
Yes.
It gives you a factor of 3 speed up.
Yes.
How? The GPUs usually have 20 instructions per byte you read or something like that.
You take the code, and I don't know I can't tell you exactly why, but no, it's a factor of 3 speed up. Yes, so if you take the code without the optimization and with the optimization and you just run it, so the only thing that I have to do to make this sort of a fair test, I need to disable unrolling automatically for the compiler, because otherwise the compiler may unroll everything and then nothing matters anymore. But if you don't unroll your loops, yes, you get a factor of 3 speed up just for checking the thing in memory.
Just quick follow-up question. How big was the two-dimensional array?
The input grid.
Yeah, the input grid. Yeah.
It's in this case it's 8,000 by 8,000 floats.
Yep.
Have you compared with a package like Halide that focuses on
For the stencils?
for stencils?
Indirectly. So we do not compare. I do not compare in Halide in this case because I just compare on lift. But the lift that you see here is the lift that was from the CGO paper, and I believe in the CGO paper they compared with Halide. I'm not sure they did, but they did quite a lot of comparisons there. So it's sort of starting from the position that, look, that already works, let's just make it better. So kind of transitively should be quite good. But I did not compare with Halide, this is just compared within lift itself. It's a lift to lift.
It's a classical answer. We did, but I'm not going to tell you more. Now, can you say more about comparison with Halide? If you know anything about?
No, I know that the results were quite good on that paper. Again, I just started when the paper came out, so I don't. I should brush up on my own team's paper.
Yeah.
About those index computations, could you give some other example? I mean, this was kind of the obvious one, which just sum over I.
Okay, yeah, sure, okay. These are the rules we added. See, sometimes I'm prepared as well. So these are the rules we've added. We say there are some basic rules, such as what do you do in case the sum is not really a sum, what do you do in case the sum has that case, and what do you do in case of a sum of 2 to the n, plus 1, but again, can be moved. And then you have rules that allow you to take sums and split them into smaller atomic bits. So, and then you have the special rules for the if then else, which is a bit complicated. But the point is that you put this system is kind of lattice-like, as in the sense you put a big sum and you eventually will come down to a situation where everything has been broken down to the smallest sums that you can. And at that point you either find one of these cases or like you're screwed. But all the times I found one of these cases. So.
But what were all the cases that you considered? Did you write this before, or did you just more or less follow some examples of?
Yeah, mostly it has been going. It has a bit and a bit in the sense that most of this one was had ad hoc because I did not, of course, foresee the idea that if then else would have appeared in my sum. The problem is more interesting than just the triangle because in the parallel version of the triangle, as I said, it's a bit more complicated the code. It has more layered parallelism, so you have arrays within arrays, and then you're chunking them. There is a modulo somewhere popping up, so it's a bit more involved. But yeah, mostly complicated version of this. You had a case where a big sum, if you're interested in this kind of thing, there was a case where a big sum ended up on the upper bound of a big sum, but then that got simplified, and then that allowed the big sum to be simplified. So that I thought was cute. Yeah.
So, can I ask a fuzzy question?
Yeah,
in the sense that it seems from the examples mostly you were talking about finite maps from an index space, some kind of space that happens to be made up of tuples of numbers.
Yeah.
Some people might like Napierian functors that are
finite,
right? So,
definitely going to use that word now that I learned
I'm
it.
just thinking of those finite maps.
Yeah.
So, and can I think of them as basically saying, okay, so many applications seem to the case that you implicitly extend in the application. I'm asking that the other indices are actually mapped to 0 in some kind of vector space or something.
Okay, no, okay. So there is one
Do you have
significant.
examples where
Okay,
you
there
don't
is
have
one significant omission that I have for simplicity on the slides. Where our system tracks the sizes of values. For example, this is the only case where this kind of flows through. For the n, we know that the n is going to be in a given range. So we know that the function is going to be in a given range. So you say n is 5, then I know that the function is to be from 0 to 4, because the function is going to be whatever the n is minus 1. And then I know the output, the size of the elements is whatever the sum of the sizes of the f outputs are. So yes, everything is going to be accounted for. So it's not that everything else is supposed to be 0, it's that the type system knows the sizes of every element, of all your inputs, and everything else is determined based on that. And therefore, you are never going to be unaccounted. You're never going to have, I give a function, but I don't tell you what's the value for a given element, or if an element comes in the function outside its domain. That never happens. Because really, this is lambda I for all I in 0 up to n minus 1.
Let me ask you another question then. So, can I think of this as saying like you have in this domain, and the job you want to do is like you want to have an isomorphism to a linear domain, like an initial segment.
Yeah,
right?
yeah.
and you want to make sure that you get a very efficient computation in the isomorphic image of the original domain, such that you can avoid lots of checks of
Yes.
inputs.
Okay, no, I would say that the efficiency bit is a bit orthogonal to the type system. So the type system just gives you the tools to say, this is the data, that's how you organize it. And because of parallelism, because we like our parallelism to be sort of nested parallelism and on the structure of the data, and we follow this map over things for loops, so your data shapes, influences a bit the parallelism, we give you tools to play with your data so that you can shape it in the way you want. Now, whether this is beneficial or not, it's sort of agnostic. Now, what I show here is that if you use this system, you can take a problem where before you had good performance, but you couldn't really express this 3-4 loop structure. Now you can, because you can cleverly shape your data, but this mechanism, you could express stupid things if you wanted. I just saying how to organize the data.
Okay. Last questions? Thank you very much.